It's 4 o'clock. Hello, everyone. My name is Zhejiang from Peking University. Let me first introduce our speaker today, Professor Tai Jin from Zhejiang University. Professor Tai Jin is an associate professor in School of Aeronautics and Astronautics at Zhejiang University, China. He obtained his PhD degree in energy and combustion from Zhejiang University in 2015. He then stayed on from 2015 to 2019 in Zhejiang University as a postdoctoral research fellow. During this time, he visited University College London and collaborated with Professor Kai Hong Luo on CoolFlame from 2016 to 2018. His group mainly focused on numerical simulations, DNS and LES of multi-phase flow and combustion, which are involved in gas turbines and high-speed combustors. His talk will be focused on a novel spray flamelet tabulation method considering evaporation effects. Okay, Professor Jin, please.
Hey, thank you very much, Professor Chen. Thanks for the kind introduction. I'm Tai Jin from Zhejiang University, and I'm great honored to be here to give this talk on behalf of our colleagues and students. My topic today is a lower spray flamelet tabulation method considering evaporation effects. This work has been done by our PhD students, Mr. Yichen Wang, and we are in the group of Professor Kun Luo and Professor Jian Fan in Zhejiang University. Okay, first, as we all know, spray combustion is very widely used in aero engines, in internal combustion and energy power systems. And turbulent spray flames are very complex, involved multi-physics and multi-scale phenomena such as the atomization and the vaporization and the fuel and air mixing, and then combustion and also pollutant formation. In our group, we have been focused on all the physical process from the atomization from jet and the evaporation and also multi-phase combustion. We have been done this for over 10 years on simulations of multi-phase combustion, and this phenomena is quite complex and also introduce great difficulties for numerical modeling. So first is just brief introduction of turbulent combustion modeling. As we all know, the lens simulation and LES simulation and the dynamic numerical simulations for turbulent combustion. For lens simulation, they use coarse measures and the full range of dynamic scales modeled. And for LES simulation, the energetic scales result and the subgrade scale dynamics modeled. And for both of these numerical approaches, we need to close the subgrade turbulent combustion, the turbulence and the chemistry interactions. This other simulation method is direct numerical simulation. Actually, for this kind of method, low subgrade modeling required, but it is still limited on range of scales. And from lens to areas and the DNS, the cost and the resolution is increased, and although DNS is very accurate, but is still limited to very simple geometry and simple physical problems. And here there are many kinds of methods to simulate the spray combustion, in such as Euler-Lagrange simulation or Euler simulations. Here in this talk, we focus on the Euler-Lagrange simulations of spray combustion. In this framework, the gas phase is resolved in the Eulerian framework, and the liquid phase jobless chart in the Lagrangian framework, and the interaction between the gaseous phase and the jobless, the coupling are described with these source terms. And here for the reaction, there will be reaction source terms in the entropy equation, and also the species transport equations in the gaseous phase. And these equations are for the direct numerical simulation. If we use large eddy simulation, the equations will be filtered, and for example, the filtered species transport equation here will got two unclosed terms. First one is turbulent transport flux. And this will use, we need to use turbulence models to close this term. And another term is turbulent reaction rate. And for this one, we need the turbulent combustion models. And up to now, there are many kinds of turbulent combustion models here for premix flame and the long premix flame. And among these, the flamelet progress variable method it has been developed over 40 years, and has achieved a lot to for the simulations of turbulent combustion. This is a general framework of the turbulent combustion model with flamelet model. First, the flamelet structures are pre-calculated, and the calculated structures for the diffusion flame, the laminar counterflow gaseous flames are pre-calculated, and then the results will be tabulated to form a flamelet library. And in this figure, we can see that the safety code coupled with flamelet library. For the safety code, we solve the transport equations of mass conservation and momentum, and also energy, and other questions such as progress variable and mixture fraction. And then the species concentration will be interpolated with flamelet library, and this is a way to get the species mass fraction from the library. So this kind of flamelet modeling has been widely used. But today our topic is about the spray flamelet tabulation. So let's go back to the studies of spray combustion with flamelet model. From the very beginning, the direct approach or the simple approach is to model the spray combustion based on the gaseous flamelet library, and this is a equation of equation in the mixture fraction space this equation is solved for the gaseous flamelet library. And actually, this is there's a big assumptions for this use. The assumption is the interaction between droplets and flame. There is no interaction, and before the ignition or before the burning of the gases, the droplet will evaporated totally. So this is a very very large assumption, and actually for the gases flamelet simulation has been done for many kinds of applications. But if there is a strong interaction between droplets and flame, there will be evaporation in the reaction zone. And this has been noticed by other researchers, such as Coolers. He suggests introduce total entropy as one of the tabulation variables, and this will include the evaporation effects. And also in this approach, they will calculate different temperature of the fuel and the oxidizer, and then tabulate this the flamelet, but it's still in the gaseous flamelet library framework. So let's look at this case. If this strong droplet and the flame interactions, we set up this configurations. This spray jet in the closed flow. And here we look at the results from the direct numerical simulations. We can see that this is the evaporation source, evaporation rate here for the blue legend, and we can see that the evaporation is overlapped with reaction. There will be two reaction zones here, and here for this reaction zone, we can see that this significant droplet flame interaction occur. And if we do the priori analysis of gaseous flamelet tabulation, we can say that from these two figures, we can see that the temperature here is over predicted by the LPV model, and also we can look at the species here. We can see many of the species are over predicted by the LPV model. So that's the issue for using gaseous flamelet tabulation to simulate this spray flame. So next we'll go back to the laminar counterflow spray flame. We all know that the flame calculation is based on the laminar counterflow flame. So we go back to as we analyze spray structure in the spray structure for the counterflow spray flame. First, we look at the spray flame structure in physical space, and here with some two reaction zone, we can see here this green one is marks reaction rate. We can see two reaction zone in this case, and we also can say that the evaporation rate overlaps the first reaction zone, and this second reaction zone is here. This what is shown droplet flame interactions. And if we look at the structures in the mixture fraction space, we can see that for the OH concentration, we can see that the two reaction zone and also the heat release rate. And we can find another phenomenon is that the mixture fraction we always use in the gaseous flamelet calculation. The mixture fraction for the spray flame will be 0 in the spray side and also in the oxidizer side. And this means that for one mixture fraction, there will be 2 branches for the red one and also the blue one. If we separate these 2 branches for the gases side or for the spray side, the red one behaves the gas side, and the blue one marks the spray side, and the mixture fraction will be from 0 to the max of the mixture fraction, and the max of the mixture fraction and to 0. If we use this mixture fraction to tabulate the flamelet, we got 1 mixture fraction and 2 temperature, and 1 mixture fraction and 2 mass fraction. So this is a problem. So one approach is to separate the gases side with the spray side, but here you need to some criteria to separate these 2 sides, and also the maximum value of the mixture fraction is not known earlier. So this will be the problem for the flamelet tabulation. So the one question is about the mixture fraction. The mixture fraction is non-monotonistic. So so there have been some methods to overcome this problem. So first one I just mentioned, to split the flame structure into a spray and a gas-sided part. This is one approach, and also there will be effective compensation available, like this one, the mixture fraction C here, and also some researchers use cumulative mixture fraction, and it's just kind of approaches can somehow overcome this problem, but it's too complicated to implement in simulations. So this is the first issue of the first question. So another question about the spray flamelet tabulation is that droplet evaporation occurs on the spray flame structure, and here for this question we have derived spray flamelet equations in the mixture fraction space, and we can see here, compared with gases flamelet equation, there will be evaporation terms in this equation, and here in previous study we can there have been analyzed different terms contribution to the flamelet structure. We can see from this figure, we can see that the dissipation term and the evaporation term and the mixture evaporation term, we can see that the evaporation term is quite large, and which cannot be ignored actually. And okay, so from this study, we can see that droplet evaporation is of great importance in the spray flamelet structure, but is not considered in previous gases flamelet library. Okay, so to overcome the first question for the mixture fraction, we have derived a new definition of mixture fraction, which we named the carrier mixture fraction here, and the carrier mixture fraction is defined here to avoid the problem related to the problem. We can see that for this laminar spray counterflow, we can see first the results that the mixture fraction, the carrier mixture fraction here, we can see that is from 0 to the oxidizer side to 1 on the fuel side. So this perfectly resolves this problem. And how to calculate the mixture fraction is actually quite simple. The equation for the carrier mixture fraction is here. And here the MF vapor is mass related from space droplets due to evaporation. So this is this will change along the axial distance, and this two MOS1 and MOS2 is the mass of the carrier gas from the space side and the mass of the oxidizer from the oxidizer side. So this very simple to calculate this carrier mixture fraction, and it's very simple to implement. So the other question is how about the flamelet structure in this new defined mixture fraction space? So we again we describe the mass fraction and the temperature, mass fraction of species and the temperature in the new defined mixture fraction space. You can say that the gas side and also the spray side here can be very clearly separated, and this one we can it meets the demand to for the one mixture fraction and one temperature. So it's quite useful, and we don't need to separate the gas side and the spray side. Okay, so this answer to the first question for the mixture fraction. Okay, so we have the mixture fraction definition. So how about the flamelet equations in the new defined mixture fraction space? So we begin with the species transport equation here, and also we applications the rules and the definitions is quite similar to the derivation of the flamelet equation in the original mixture fraction space. And then we can got the species transport equations in the J carrier space here. And also we can got the transport equations of the carrier. So so this from this two, we got the spray flamelet equations in the J carrier space. So this is so this is the final spray flamelet equation. So for the pre-calculation of the flamelet, we need to solve the last question. The last question is how to calculate this equation. We know that for the gaseous flamelet library, we can calculate the this equation in the mixture fraction space, or we can calculate this in the space physical space. So for this equation, I think the very simple one is to calculate the one-dimensional flames in the physical space, because the mixture fraction space, the calculation of the mixture fraction space, we are still ongoing to develop methods. So here we will take the simple approach to calculate the spray flamelet equation in the physical space and then tabulate the flamelet. Okay, so to summarize the steps to overcome the questions about the spray flamelet models. The first is we define a new carrier mixture fraction, and it's quite easy to implement in the code to solve the Gaussian equations, and we then derive the spray flamelet equation in the J carrier space. And at last, we will tabulate the spray flamelet tabulation. We will calculate the transport equations of carrier mixture fraction, and also the original mixture fraction, and also the progress variable. And then the spray flamelet library will tabulated in the space of carriers mixture fraction and the original mixture fraction and the postgress variable. And this new model we named is tabulated display of flamelet progress variable model. Okay, let's go to the TSFPV model. So this is a flow chart of TSFPV model. So it's quite similar with gases simulations. The difference is about the Lagrangian check of the jobless. This is different, and another difference is how to tabulate the flamelet, and we have discussed about this, how to tabulate the flamelet simulations. So the last question is how to calculate the flamelet. Oh, this is the last question. So before the direct approach is to calculate the laminar spray counterflow flame. We can calculate series of spray counterflow flame, and then we can extract the solutions to make the flamelet library. But the question is for the droplet in the spray counterflame simulations, the droplet, the parameters of the droplets will be varied a lot, such as the droplet velocity, the droplet size, the global equivalential ratio, and also the temperature of the droplets. So all these parameters, they are needed to integrate it to the flamelet library, because if the velocity of the droplet is different, the flamelet structure will be different. If the droplet size is different, or the global equivalence ratio is different, the spray flamelet structure is different. So in this way, you need to calculate loss of counterflow flame, and also the flamelet library will be very high dimensional, and also very complex. So how to solve this problem? So this problem, this is a key to the TSFPV. So we have derived the spray flamelet solution here. You can see that if we take this gaseous phase, gaseous phase equation, we can calculate the transport transport diffusion one, and also the reaction rate. And the reason if we can find this evaporation source term here, so this is unknown. If we can calculate this source term, and this source term is related to the droplet parameters, such as its velocity, such as size, such as its temperature. So all these parameters will come to this source term. So in this way, we can just calculate this gaseous flamelet equation. So the method is to calculate the 1D laminar gases counterflow flame here to calculate the flamelet. So and this will get very simple calculation of the flamelet. So there will be another question to how to calculate this evaporation source term. Actually, is related to quite a lot parameters of jobless. So later I will discuss the two approaches to close this evaporation source term. The first one is quite simple, but it's simple that actually we have got the direct numerical simulations of laminar spray counterflow flame. Is that right? Yes. So we can actually the source term from the DS results, and we use this data. We have this data, and we can analyze this data, and we fit it an equations for the source term, and we got the equations for the we got the equations for the source term, and the source term this equations is related to the carrier mixture fraction, the carrier. We can say that from this figure is quite related to the carrier, and is so we got this formulas, and so in this approach we can just in the spray flamelet equations we just use this source term and its relation with carrier mixture fraction. So that's a solution of the problem, and this is a routine to tabulate the flamelet. This way is quite similar with gases flamelet. We can calculate different flamelet with different source terms, and then we can tabulate the flamelet library in the space of carrier mixture fraction and original mixture fraction and the progress variable, and then we got the final spray flamelet library. We have got the formulas for the source term. So we got the Euler analysis, and here we compared with the original PV model and also the RP model, which consider the entropy collection. So we can look at the temperature profile. We can see that for the gases PV model, because it can't distinguish the spray side and also the oxidizer side. So the temperature for the RP model is the same, because the mixture fraction for the two sides is 0 for the two sides. So the temperature is quite long, and for the PVH model, we can say that the temperature for the spray side can be collected. However, the reaction zone, the temperature of the reaction zone is over predicted, and we also and for the TSP model, we can say that it's the agreement is quite better, and we can, if we look at the other species mass fraction, you can see that also for the intermediate species, the TSP model, the results from the TSP model is better than the other two models. So from this results, we can see that the evaporation effects need to be considered for this for the calculation. And then we also do post-linear analysis, and we have discussed that the LP model is not the deviation of LP model is quite large. So we compare the TSLP model and also the LPVH model. And for the posterior analysis, we can also that the better performance of the TSLP model. So let's go back to the let's go back to the 2D display flame, and this is showing interaction of droplet and the flame here, and we compare the TSLP model and the LP model. We can see that the low temperature between the two reaction zones can be well captured by the TSLP model, and also if we look at the mass fraction of species, we can also the performance of TSLP model is better. Okay, also we do the post-linear analysis, and we compared the results. We compared the results with direct numerical simulations. We can see that the results generally agree well with the direct numerical DNS results. And okay, so this is a statistical analysis. From these figures, we can see that agreement is quite good. So in this up to now, we have derived the display flamelet equations when we have closed the evaporation system with an empirical formulas. This formulas is fitted from the data from the DNS results, and if we use this approach, it means that you need to first do some kinds of DNS simulations of the laminar counter display flame, and then we fit this formula, and then we use this formula to close this system. So it means that we need to do extra computation, and the formulas also lack of generalization. So this is the first issue of until now, and also this another issue. It will be related to the spray jet flame. We'll discuss this later. So we ask the question, if is there any theoretical models can predict the system, and actually there have been done some calculation by other researchers, and they have do some theoretical analysis of the evaporation source to the other parameters such as velocity, the number density, and the mass density, and other parameters to the droplets. So from this analytical calculation, they have got a theoretical model for the system. This is here, and the detailed derivation of this procedure has been shown in our paper. And here we call this is a theoretical spray evaporation system, is a CST model, and we use it. And in this case, we can calculate this system, and we don't need to do pre-calculation of direct numerical simulations. So let's first check. This model. We take two DNS of spray flame. One is the diameter of droplet is 20 micrometer, and the other one is 40 micrometer. For these two cases, the first case is that the droplet will evaporate totally before the reaction, and the other case will be two reaction zone, which means that the interaction between droplet and flame is strong. So we take this DNS results to test the SCST model. These are some parameters calculated from the DNS results, and we look at this picture. We can see that the SCST model results is quite similar with DNS results, not only for the single reaction zone case, and also for the two reaction zone case. We can see that it's quite agree with the DNS results. So this is a priori analysis of the SCST model. Okay, we also do the posterior analysis, and this figures has shown that the SCST model can also reproduce the source term. We can see that the comparison with dotted line and also the line with calculations, and these two lines are agree well between each other. So okay, so this is the first solution to the first issue. So we have got the synthetical model for the source evaporation system. So until now we have validated the model with DNS results. So next we will validate the results. We validate the models with experimental results. We have chose this setting turbulent lifted masonite spray flame for calculation. This is a lifted two-phase flame, and with air and the spray, with air and the spray in the center, and with aided cold flow in the cold flow, and the flame will be lifted. So these are the inflow parameters for the experiments. There is another question I have just mentioned, that for the spray, for the droplets and air in the central jet, there is some pre-evaporation of the spray, which means some of the droplets has been evaporated in the central jet. And also we can see that from the inside of the jet, the droplet will be evaporated gradually, which means that in the central jet there will be not only the droplet and also the vapor which has been evaporated. So for this case we need to distinguish this vapor mass fraction and also the droplet. So here we introduce another parameter, mixture JF, to calculate to describe this process, and we need to calculate different flamelet with different vapor concentration, and with in this case we need to calculate different flamelet flamelet simulations from this J-jet to the J-max, and here for the J-max, it means that all droplets are evaporated, and all the mixture fraction is from the vapor. So these are different flamelet need to be calculated and then tabulated. And here for this case, we use the SEST model to close the evaporation source terms. Here, before we have described the implementation of the TSP model in the framework of DNS, which means that we don't need the tabulation models. And here for this case, we implement the TSP model in LES, and this is how to implement. We have to solve 5 actual transport equations. It was there are mixture fraction, original mixture fraction, the progress variable, and the carrier mixture fraction, and its variations. Just 5 actual equations, and the other routing is quite similar as before for the gases flamelet. And first we look at if we would like to look at the results, we take into the JF parameter. We can distinguish the 2 reaction zone and the 1 reaction zone and the totally gases flamelet. So this results we introduce mixture fraction for the pre-vaporized simulation. And this results for the calculation and compared with experimental results. And we look at the lift of height for the simulation results. For the calculation is about 20.4 diameter of the jet, and for the experiment is 21 diameter, is quite close. And we then compared the results of the temperature at the different actual positions. We can see that the results is greatly improved using this TSP model, especially for the central region. Here the central region actually for the due to the evaporation effect, the temperature at the central region is quite low for this kind of flame. And with this TSP model, we can actually accurately calculate this phenomena. And for other results downstream, we can see that the results is quite better. And also we compared the velocity of the particles or the droplets. It also agree well with the experimental results. And also this is a parameter of the droplets. They are quite agree well with the experimental results. So in summary, in this works, we have done 3 things. So the first one is we define a new carrier mixture fraction, and this new carrier mixture fraction can better describe the temperature and the species mass fraction of the flamelet, and then the flamelet library takes into account the effects of droplet evaporation, and we have used the modeled the evaporation source terms with empirical formulas, and also a theoretical SEST model has been derived. And these 2 models can give very good results for the evaporation systems. And at the last, the TSLP model is systematically evaluated both for the DS results and also the experimental measurements. And the results have shown that the agreement is quite well. And we are looking at that the bigger future of the using of a TSLP model for spray combustion modeling. So this is the end of my talk, and this some of the details has been skipped, and if you are interested, you can refer to our two papers. The first paper has been published in field, and some results also submitted to combustion and flame. So this is the end of my talk. Any comments and questions are welcome. Thank you.
Okay, thank you, Professor Jin, for the wonderful talk. Now we will go to the Q&A session. So if you have any questions for Professor Jin, please send your question in the chat box, or if you're a panelist, you can open your microphone and ask yourself. Okay. Let me see. Okay, let me ask a question first. I think this is a substantial improvement from the existing flamelet methods or chemistry tabulation methods for spray combustion. My question is, for the parameters you need for this new flamelet model, spray flamelet model, how can you comment the generalizability of those parameters if you go to a different configuration or boundary conditions?
Yes, that's a very good question. So I think the main idea for this new model is to avoid the complex boundary conditions, or especially for the various parameters for droplets. So all the parameters for droplets, they will be come to just one term is evaporation source term. However, the evaporation source term is from this slide, we can see that the evaporation source term is related to some parameters, and we can change this one. We just change this one, and we don't need to know how it related to the diameter or the number density and some other parameters. We can change this one, and we got different flamelet calculations with different evaporation source terms, and then we can calculate different flamelet structure, and we extract the results, and then we tabulate the flamelet library. So I think this is a true idea for this new approach. It involved the difficult to calculate loss of simulations of spray counterflow spray frame with different parameters of droplet.
Okay, okay, thank you.
Hello, can I ask a question?
Oh, sure, please go ahead.
Yeah, okay. So Professor Jin, thank you very much for a very nice talk. So I think in one of your slides, you mentioned if the droplet actually is very small, then they can be fully vaporized, right? Before they directly interact with the flame reaction front, right?
Yes.
Yeah, so for that case, actually, probably, you know, the flamelet, probably we can directly use a gases table.
Yes.
So do you identify the critical diameter homogeneous
Yeah.
table, say gases table or table, right? I need it.
Yeah, that's a very good question. Actually, I think it depends. We don't get the criteria for this question, but I think it depends on various parameters, such as if you look at the laminar counterflow split flame, it depends on the boundary conditions for gases, for also for the droplet. So maybe if we have done many DNS simulations, we can come to the criteria, but this criteria may be just related to this setup of the boundary conditions. I'm not sure it will be general for different conditions, but also just I think this is a very good question. For this new approach, we can deal with these two conditions. As for the cases with small droplet, there's no interaction between droplet and flame. So the evaporation system will be given to, or we will come to 0 for the flamelet calculation. So in this case, we can calculate the two conditions. But if how we can get the criteria, I think it is maybe there will be some theoretical calculations. So they can got the maybe from this calculation, maybe we can get some further derivations. So when will be the evaporation system come 0? And I think this one is related to the boundary conditions. So maybe in this way we can get some criteria to distinguish the single reaction zone and the double reaction zone.
Okay. Okay. Thank you very much. Thank you. Yeah, this is my question. Okay. Thank you.
Thank you for the question.
Okay.
Okay, no more question.
I think I have another question actually. So in your actual lookup table, how many control parameters do you have?
Just 3. Yes. So
it's the Z carrier, Z and C.
Yes, just 3.
Okay. How difficult is it to actually map your original canonical solutions to this 3-dimensional manifold? And do you have any non-bijective, so this double value problem? Do you get this kind of problems?
Actually, the routine is the routine is simple, but we do come across some problems for the tabulation. And we actually this not directly mapped to the space of the carry and the J and C. And before we need to first to calculate some also some more chemical quantities that will be described with the carry and this gamma low and also A. So this is different, and also this is the actual cost for this method, and then we can remap this one, remap the temperature and the space mass fraction in this table. So for the 1.2 or the objective problems is no objective problem for this method. So this is I think this is the advantage of the definition of the carrier mixture fraction, and we not only use this one to the spray calculation, combustion calculation. We also use this for the polarized coal combustion. It works well for the definition.
Okay, thank you.
Can I ask one more question?
Sure.
Yeah. So Professor Jin, I think at the last part of your presentation, you simulate the jet flame from Sydney, right? So in this, so here the actually this system is 3-stream system, right? Spray and air and cold flow, right?
Yes.
And here the carrier gas is air, and at the same time, we also have the hot cold flow, right?
Yeah.
So in this case, do we need to did you distinguish the air and cold flow in your simulation, in your table?
Yeah, sure. Actually, for the visualized cold flow, it will be also mapped to the J carrier and the J and the C space, and the boundary for the visualized cold flow is described not by the species concentration or not by the species concentration, but by the progress variable for the mixture fraction. So yes.
Okay. Okay, thank you.
Okay. Any other questions from the panelists or from the audience? Okay, maybe I can ask one final question, which is slightly more practical. Do you see any difficulties if you use this method for swirl flames?
I think there will be problems, but I'm not sure. Actually, for the swirl flames, the flamelet, if we just use this flame, the same flamelet model, I'm not sure there will be any other problems. Actually, there have been good example to use gaseous flamelet model to simulate the swirl gaseous flame, and sometimes the results is not good. we are not sure the result, the deviation is from the flamelet model or from the turbulence model. So actually, for the swell flow, the turbulence model is very important. So so I think this model can be strictly extended to swell spray flame. I'm not sure how the results. Actually, there have been many improvement for the gaseous flamelet models, such as the models which can consider the differential diffusion effects and some much more complex flamelet models. And in this, until now, we just extend the gaseous flamelet to the spray flamelet. I think we deal with a big problem. There still remains problem about unit Lewis number and some assumptions about flamelet equation. So this problem will I think is common for the gaseous flamelet or spray flamelet. And in our case, it overcomes the problem to deal with the calculation of spray flamelet. If you just directly calculate the two-phase counterflow flame, it will be very, very expensive, and it's not easy to it's not easy to map this results to the flamelet library. So we overcome this problem, and the solution actually is not so complex, and that's I think it's with what we have done, and we will see how it works in much more complex combustion configurations.
Okay, thank you. Any more questions? Okay, if not, let's thank Professor Jin for this webinar, and the panelists, if you can, please open your camera and we can say goodbye to everyone. Okay, thank you.
Thank you. Bye bye.